Hello and welcome back to Calculus 1 section 3.9 on derivatives of exponential and logarithmic functions. Our goal for today is to learn these in depth, to see not just the base e, which is e to the x or ln x, but also to see other bases than that. So we're just going to use the letter b as any base. Now, first we start with exponential functions, and we start with what we know. So exponential function. Now, these are all obviously derivatives. What you learned before is that the derivative of e to the x is e to the x. So the derivative is itself. Then we made this a little bit spicier by saying, well, how about if you have some constant in front of it, and that by chain rule turned out to be just that a goes in front. So at first we memorized that, but then when we did the chain rule, we know that that a is the derivative of the exponent, right? Derivative of ax is a. So we know where that comes from. And then now we would like to have e to the f of x. And this is your boss equation. This is the one that you need to know at all times, because 99% of everything you ever do will be in this form. And that is simply e to the f of x times f prime of x. It's a standard chain rule that you always have. That's it. Now I'll do this. Because, and I'm labeling this one as, the most important, the alpha and omega of everything, just because sciences mainly have exponential function represented as e to the whatever value. And then if most of the functions are there e, right, then you need to take derivative for, to measure the change or whatever. So this is why we want this one. And this one is the most important one. However, that's not the general case, right? General case is the derivative of any base to any function. So this is our derivative that we are trying to learn, and we're going to try a couple of problems as well. And that one is going to be b to the f of x times f prime of x times ln of b. Now, this is your general case, but as I said, it is very rare to run into a derivative that is, exponential function, say, 2 to the sine x. It's rare. Someone really needs to go out of their way to make that for you, like we do on exams, just to see if you know the concept. But you're not going to find it in nature, right? Nature goes with the natural number e. So if you take this formula now, and I already mentioned the example, so let's do that one. 2 raised to the sine x. Well, if you follow the formula, you know that f of x is sine x and the b is 2. You literally just need to fill the formula the same way. So you can see that this is the same. So Control C, Control V, there we go, times the derivative of sine, which is cosine x, and then ln of the base, which is ln2. So if you want to make this pretty, the only thing you need to do is to put ln in front, because we like to have the constants first, and then we have exponential before trigonometric. That's another, these are not rules, it's just the way the people, write it. So there it is. That's the answer. There's nothing more to it. Much more important is your ability to take the derivative of, let's say, e to the negative 6x times the cosine of, let's say, 4x. So if you are going to take physics, if you're going to take mechanical courses and so on, you're going to see a lot of functions like this, because these are the functions that model that motion, the motion of the pendulum, right, as it swings left and right, or if you hook up something to a spring and let it, you know, bounce around with the spring. These are the equations that govern that. So over here you see the product rule, and then you see the two chains, but the fact is that you are using this e to the negative 6x, which is the most important, right, out of all of these, is the most important one to know. So now, since this is a product rule, we copy the first. Then we take the derivative of the second. The derivative of cosine is negative sine. So we have negative sine 4x. And then we have to multiply by the derivative of the function that is buried within the sine, which is 4x. So the derivative of 4x is just 4. Again, there is that dx, but we don't write that, so don't worry about it. So that's copy the first, derivative of the second, and now plus, copy the second. We're still in a product rule. Copy the second, and then derivative of the first is just negative 6. So, oops, we can factor out 2e to the negative 6 x, and then put the rest in parentheses. Now, as you can see, I could have factored the minus as well, so they all become positive now. So from the first parenthesis, I took this out, and I took 2 out of 4 out, and I took the minus out. So the only thing that it stays is 2 sine 4x. That's the only thing that stays in the first term. E to the x is out. Out of this 4, 2 is out. The negative is out. So the only thing that stays here is 2 sine 4x. Same thing goes for the second parenthesis here. I am taking out negative. I am taking down e, and I'm taking 2 out of 6, leaving 3 behind. So it's going to be plus 3 cosine 4x. There we go. So what is this? Well, if the path function was described with e times the cosine, the derivative is the velocity, because that's how fast the object is moving, and you can also figure out the direction and all other things, but that's not for this lecture. So as long as you can do these things, you are in a good shape. Look at the problem, decide whether it's just implicit or it's just product rule or just quotient rule or mixture of some of them. That's very important. And just do tons of problems. This cannot be learned by observation of what someone is doing. It actually has to be your struggle that figures it out. That's how you make your neural connections in the brain, by repetition, right? So just do a whole bunch of these problems and you should be fine. We are going to switch now from exponential function, which is literally that's it, to logs. So what do we have here? Well, derivatives of log functions, ddx, there we go. How about we put that red as usual? There we go. Do I have to fix the exponential? Yeah. All right, fine. Here. We took the derivative of that. All right, so first of all, you're in Calc 1, and you should know everything about logs to perform well in many of the sections coming up that will have logarithms, especially when you are in integration. Now we'll see why and how, but it's very important to be very comfortable with logs. Now a lot of people say, oh, logarithms, that's the function. No, it's not. Logarithm is just a basic computation, like any other computation you guys have that you do between two numbers. So if you talk about 2 plus 3 equals 5, then you can go 5 minus 2 equals 3 and 5 minus 3 equals 2 to retrieve 2 and 3, which made 5 in the first place. 2 times 3 is 6. 6 divided by 2 is 3. And 6 divided by 3 is 2. So we do have an operation, which is multiplication. You memorize those tables, and you go from there. And if you need to retrieve any one of them, you have the opposite operation, which is division, and that one is now 6 divided by 2 is 3, and 6 divided by 3 is 2. And the final upgrade over here is 2 cubed is equal to 8, because 2 times 2 times 2, right? It's 3 2's. And when they all multiply, you get 8. Now, when you want to retrieve some of these values, right, you can go and say cube root of 8 is 2. So you were able to retrieve 2. How do you retrieve 3? And for that, we use logs. So log base 2 of 8 is 3. And now see, I was able to retrieve both of these just like before when I used the opposite operation. Now, it turns